Could you just check if there's a... Okay, just talking, I see. If
Okay,
not, there's something you need for that.
Okay.
Sorry.
Okay, no problem. Sorry for that. Okay. And just to explain to you one way where I use this kind of notation, this quantity psi h in v psi, it is the energy of a set of electrons that I've just written to you before, when the state of the electrons is described by wave function psi. Okay. So just I hope you will not be too much perturbed by this notation, but okay. So let me now switch to density functional theory and what it is about. So to introduce you this theory, I need to introduce another quantity. So assume that you've got a set of n electrons, the state of which is described by a wave function psi. You can define the electronic density associated to the wave function psi, which is a function only defined over R3 and not R3n as is a wave function, okay? And it is equal to the integral of the squared modulus of psi on all variables except one, basically, up to the n factor that is here, okay? And it gives you basically the probability of finding one electrons into the space R3, okay? And then you've got the following very nice result by Hohenberg and Kohn, which was made rigorous in mathematical terms later on, which states the following thing. Eg of V, remember, was the energy, was the lowest possible energy of my state of electrons, the ground state of my energy of my set of electrons. So this ground state energy, you can express it as a minimization problem upon a set of electronic densities instead of electronic wave functions, as was originally the case in the many-body Schrödinger problem. Okay, and so more precisely, you can recast it as the minimum of some functional, which reads like this quantity fhk of rho I'm going to detail later, plus the integral of the external potential V times rho on the set of admissible electronic densities. So I'm going to detail these two quantities, fhk of rho and the set of admissible electronic densities later. But first, let me make the following remark. If you consider this minimization problem instead of the many-body Schrödinger electronic problem, of course, from a numerical point of view, it is much easier to handle, since you only have to optimize upon functions defined over R3 instead of R3n. So you've got a hope to circumvent the curse of dimensionality by considering this minimization problem instead of the previous one. Okay? Then I've got to make two points. First, what is this set the electronic densities has to belong to? So these are the set of possible electronic densities that come from an admissible wave function. And what is nice is that you can have an explicit characterization of this set, which was given by Levy and Lieb, and which reads as follows. So you do not have to go back to a wave function to devise an admissible electronic density. So that's a very nice thing. But there is still a catch. There is still a catch in the sense that here, in the functional to minimize, there is this quantity, fhk of rho, which is called the Hohenberg-Kohn functional. And actually knowing the exact value of this functional amounts to solving, again, a high-dimensional problem. Okay, so this is the catch. Unfortunately, there is no free lunch if you tackle this directly. This Hohenberg-Kohn functional, it's still for a given electronic density rho. It still writes as the solution of a minimization problem defined over the set of wave function. That's life, too bad. So here I just want to say that here what you minimize is the quantity with the two first contributions in the energy. Sorry, I'm going back here, which is the sum of the kinetic term and the Coulombic term without the external potential term. Okay. So at least it has the advantage of being independent of the external potential. Okay, so what have we won there? Yeah.
Is there a reason to have the n? Why is it that density?
It's a question of normalization in the sense that the classical choice is to choose the electronic density so that its integral is equal to the number of electrons. That's yeah, and not equal to 1. But that's somehow it's a it's a choice that what's classically done. You could do exactly the same thing by taking this n, okay, and you would have an n appearing here, okay. But I mean, it's a matter of let's say of habit and definition. Are there other questions? No. Okay. And so in the chemistry literature, well, a lot of work has been done by chemists and physicists in order to find approximations of this Wendell functional that are easily computable. And then to use these approximations, instead of the true Wendell functional in this minimization problem, to obtain some approximations of the ground state energy. And so here there is, in the chemistry literature, there's a wide zoology of such kind of approximations. I will not enter into this because it is a huge jungle, okay? I'm just mentioning, for instance, Concham LDA. So Con obtained the Nobel Prize in Chemistry for the approximations that he developed there, okay? So this, and all these functionals, they have a range of molecules for which they work well, for which they do not work well, and there are different reasons for choosing one approximation or another for different types of systems. Okay. Here I'm going to talk about one particular way to approximate this Wendell functional, which is based on semi-classical limit of this functional, and which yields to an optimal transport problem I'm going to explain to you before. Okay. So it's one particular way to approximate this Wendell functional. Are there questions so far? Okay. So before explaining to you the link between what we've done and optimal transport, what has been done on the approximation of this quantity and optimal transport, I want to make one remark. Okay. This functional, this Wendell functional, it is not convex. So that's not a very nice thing, because here it would mean that if you solve this minimization problem, you could in principle get into some local minima or get different values for the minimal electronic density. And this is the reason why Lieb has introduced, well, another functional which is called the Lieb functional, because he introduced it, okay, which is just a convexification of this Wendell functional, okay? So this is another functional which depends on an admissible electronic density. It's denoted by FL of rho, and you can define it this way as being the infimum of all convex combinations of the values of the Wendell functionals taken over all possible convex combinations of electronic densities. It's just made to be a convexification of this Wendell function. Okay. What is nice is that you can show with convex analysis tools that the ground state energy of the electrons is still equal to the solution of a similar minimization problem, but where you have replaced your Wendell functional by its convexification, which is the Lieb functional. And here, what is nice that you obtained, so the problem is still complicated to compute the Lieb functional, but at least it's a convex problem. And so it's when it comes to the resolution of this problem, you are on safer ground, let's say, when it comes to local minimum. Okay. And so what we've done is to propose some ways to approximate this Lieb, some mathematical results on some approximation of this Lieb functional and on its, sorry, I will go back. This Lieb functional, its value will be expressed as a solution of a quantum optimal transport, as I'm going to explain. And we've also considered the semi-classical limit of the original Wendell functional, which reads as a classical optimal transport problem. And I'm going to explain to you these two types of problems and how we can use them in order to devise approximations for this quantity. Okay. So first, let's focus on the Lieb functional. So the Lieb functional, as I told you, we can express it as a quantum optimal transport problem, and I'm going to tell you how you can see this. As I've told you, you can express it like the convexification of this Wendell functional. And there is an alternative way to express it, which is the way I'm going to tell you about just now. Here, I need to introduce some objects, okay? Here, this sigma 1 plus, okay? That will be a set of operators acting on wave functions, okay? And these operators will be self-adjoint, they will be non-negative, and they will be trace class in the following sense. These operators, I'm going to assume that they can all be diagonalizable with eigenvalues alpha I that will be non-negative. And I will assume that the sum of these eigenvalues will be finite. Okay? And here psi I, sorry, is an orthonormal basis of L2 functions, quadratic integrable functions. Such operators, they are called mixed states by oppositions to wave functions that are called pure states in quantum chemistry. Okay? And so this is a bigger set somehow than just a set of wave functions. But you can still associate to each operator that can be written under this form, you can still associate an electronic density to such an operator. And the way to construct the associated electronic density associated to such an operator is by computing it as the sum of alpha I, the eigenvalues of the operator, times the electronic density of the psi I being the eigenfunctions of the operator associated to the eigenvalue of alpha I. Okay. So if you consider such a set of operators, it's kind of a generalization of the state of the electrons, and you can still associate an electronic density. And what you can show is that the Lieb functional, you can, which is, which again is a complexification of the Weinberg functional, you can express it as a minimization problem of some quantity over the set of such mixed state operators that can be written under this form, under the constraint that the associated electronic density is equal to rho, the electronic density that you've chosen from the start. Okay. And the quantity to minimize, well, you can express it using the eigenvalues and the eigenfunctions of the operator again. Okay. So that's okay. It doesn't seem to gain anything, because instead of very high dimensional problems defined over a set of functions, we have a high dimensional minimization problems defined over a set of operators. But you'll see why I introduce them in, later on. Okay. I just want to say that this kind of minimization problems is called the quantum optimal transport problem in the literature. And then I'm going to, so keep just that in mind. And now I'm going to introduce you what is the classical optimal transport problem, which is a classical counterpart of this minimization problem. How do you get this one? You get this one by going back to the original Weinberg functional. Remember, this one was a minimization problem over a set of wave functions. And you consider a parameter-dependent Weinberg functional, which is defined as follows. Okay. Here you put this semi-classical parameter h in front of the kinetic term, and you let its value go to 0. So somehow you're building an approximation of the original Weinberg functional by erasing the influence of the kinetic energy of the electrons and only keeping the influence of the terms which comes from the Coulombic interactions of the electrons. And this is called also the strongly correlated electron limit, okay? And it's, so this guy is denoted here, and it's just a limit as this semi-classical parameter goes to 0 of the Weinberg function. And this guy, the semi-classical limit, reads as a classical optimal transport problem, okay? So believe me, this has been proved by, in particular, by people like Gero Frieseke, Mathieu Levin, and their collaborators. If you look at this semi-classical limit, so you obtain an approximation of the original Weinberg functional, which reads under the following form, okay? It reads as a minimization problem of this quantity, and I first tell you what's the minimization set. So the minimization set is upon the set of gamma, which are symmetric probability measures on R3n, the marginal of which up to an n factor is equal to rho. Okay, this is the counterpart of the electronic density constraints that you have in the original Weinberg functional. Okay, and the quantities that you have here is the integral of the Coulomb cost, the Coulomb potential, sorry, times the probability measure gamma. And so this over minimization problem, this time defined over probability measures of R3n, it's a classical optimal transport problem. Okay. So just a brief recap. We've got this Lieb functional and this strongly correlated functional. So remember, this Lieb functional yields you the exact ground state energy of the electrons, which is a nice thing. And it reads like a quantum optimal transport. So the which reads as a minimization problem over a set of operators. Okay. And then you've got its strongly correlated functional, which is an approximation of the Weinberg functional. And so will lead to an approximation of the ground state energy of the electrons. And this guy is a classical optimal transport problem. The unknown of and reads as a minimization problems, the unknown of which is the probability measures on R3n. And you've got constraints that are these electronic density constraints, which reads as follows in both cases. Okay. And so what we have done, and that's what I want to go to, we have worked on approximations of these two problems, where you can prove that minimizers of these two problems, which a priori are very high dimensional objects, defined over R3n, but actually you can prove that these approximations yield to approximate minimizers that are very sparse objects. And these very sparse objects, we are able to compute them, or at least approximations of them. And that's what I want to go to. Okay. Are there questions? No? Okay. Yeah. Yeah, absolutely. So the fact that what I want to point out is that we'll have the same kind of sparsity results for both types of problems. So I'm not saying this is the end of the story, but still it can, there is sparsity in both contexts. And the advantage here is that in principle, you've got an exact value of the approximate ground state, of the ground state energy. This is not the end of the story, but let's say that this guy is a better candidate to try to approximate to get the approximation of the ground state energy than this guy. But since they share the same kind of optimal transport structure, there are comparable sparsity results. That's okay. So just going quickly on this, if you use standard numerical methods, well, they are prone to the curse of dimensionality. And so we are not the first ones to get interested into this problem, in particular for the classical optimal transport problems. There have been several other numerical methods to try to solve them when the number of electrons is large. And in particular, there have been a lot of works by the Mo-Kaplan team group, for those of you who know them, using the Sinkhorn algorithm and entropic regularization, for those of you who know optimal transport. Okay. Not much on the quantum optimal transport problem, at least up to my knowledge. So what we've worked on is yet another numerical method in order to try to tackle this problem, and for which we can prove this sparsity structure, which is nice from a numerical point of view, even though there is a lot of work to do on the mathematical analysis side to put everything on very rigorous ground. Okay. So the idea here is to relax the electronic density constraint, okay, which is an infinite dimensional constraint on these minimization problems, by a finite set of scalar constraints. And this finite set of scalar constraints will, sorry, I'm going to go to the next slide because this you don't really need. So these electronic density constraints are the ones that I've written in this fourth equation. Okay. They will be replaced by a set of m scalar constraints, which will consist in just imposing the value of some moments of the electronic density associated to either the mixed state in the Lieb case or the probability measure in the classical optimal transport case. Okay, so to define these moments, you need to introduce some functions phi m, which will play the role of moment functions. Okay, you have to choose them well in order to have accurate approximations, and this is a whole question in itself. Okay, but assume for now that you've found m relevant moment functions to use. Instead of having the full electronic density constraint, you only impose that the integral of these test functions phi m times the electronic densities of either the measure gamma or the operator gamma are equal to the moments of the electronic density rho that you've chosen. Okay. And then if you do that, you can construct approximate minimization problems where you ask for the electronic densities here only to satisfy m moment constraints. And so these are constraints that are much less demanding than imposing that the rho gamma are all equal to rho exactly. And so this gives some different minimization problem where the minimization sets in both cases is larger than the minimization sets of the original problem. Yeah. Yeah, this phi m is a function of R3, exactly. And the rho m then is the integral of I m times the rho. Yeah. Yeah, it's a number. Absolutely. Yeah, sorry. Are there other questions? Okay. Yeah. So why do we consider this kind of approximations? But first of all, that's a kind of a sanity check, okay? What you can prove is that under very natural conditions on the set of moment functions that you take, they have to be dense in some good spaces. You can prove that as m the number of moment constraints that you impose go to infinity, then the approximate values of both optimal transport problems converge to the exact point. Okay, that's the least that you can ask for such a kind of thing. And what is interesting is that these approximations with a finite number of moment constraints, you can prove that there exists some very sparse minimizers to them. And that was our main motivation for considering this kind of thing. So let me give you the sparsity result in the classical optimal transport case. So the solution that we are after is the probability measures defined on R3n. Okay. And so for the moment constrained optimal transport problem, you can prove that one minimizer of this approximate problem reads at a discrete measure, which charges a number of points, which scales at most as the number of moment constraints that you impose plus one. Okay, so it can be written under this form. And so identifying a minimizer under this form only amounts to identifying m times n scalars. Okay. And what is nice is that here, the complexity of the number of unknowns to identify is only linear with respect to the number of electrons. Whereas if you use standard numerical methods to approximate this kind of optimal transport problems, you would have a complexity which scales exponentially with the number of electrons. Okay. So this is a nice thing. Okay. This kind of representation is sparse, but of course there is a question, do I get a good approximation out of it? Okay. And so that's something that we heavily use in the numerical tests that we've performed with this kind of approach. Okay. I'm going to skip briefly what happens in the quantum optimal transport case, but you've got a similar sparsity result with this moment constraints approximation. So just skipping that for a moment, and I'm going to, we can derive some error bounds in the quantum optimal transport case. And I'm just sticking to the classical optimal transport case for the sake of simplicity. So now a natural thing to do is to restrict the minimization set of the moment constraint approximate problem to the set of measures that are discrete and have this sparse form. Okay. And this yields to an optimization problem where you have to optimize the location of the Diracs, which are these xk vectors, and the weights of the Dirac in the discrete measure I've introduced to you before, WK. And so this reads under the following form, okay, where you have to optimize over a set of particles, n weights, okay, under some constraints, which are the equivalent way of expressing the moment constraints I've just introduced to you before. So all in all, this reads as a non-convex optimization problem with non-convex constraints, but with a number of unknowns that is smaller than what you would have obtained with standard numerical methods. So there is no free lunch. If you decrease the size, the dimension of the problems to solve, well, you've got non-convexity appearing here. Okay. So the way we've done this practically, and that's where I would be very interested to have feedback from experts in constrained Monte Carlo sampling and constrained Monte Carlo stochastic gradient algorithms. So we've used some kind of stochastic gradient algorithm under constraints here. And the way we do it is to generate solutions of these minimization problems, like solutions, long time runs, along trajectory series of overdamped Langevin dynamics on a manifold, on a constraint manifold, which encodes these moment constraints here. But we've got no theoretical guarantee of this kind of scheme. Okay, so that's and we've done a very naive way to discretize the corresponding overdamped Langevin dynamics. So here, I think there's definitely a lot of room for improvement compared to what we have tested. So I'm going to skip this and just show you some numerical results that we have done with this kind of scheme. So here, first, some one-dimensional numerical results, but with 5 electrons, nevertheless. So instead of our 3, I'm just on interval 1 minus 1, 1. And here are 3 different values for this electronic density rho that we consider. The advantage of doing this 1D numerical test is that we know analytically the solution of the exact optimal transport problem, and so we have some reference to compare to. And this is the kind of plots that we obtain. So this is for first electronic density that is just a uniform density here. These red diagonal lines, there are some marginals of the solution of the exact optimal transport problem, which is here a probability measure over R to the 5, because there is a minus 1, 1 to the 5, because there are 5 electrons. Okay. And these blue dots that you see are the locations where the stochastic optimization algorithms that we used, they show the location of the points of the discrete measures that we obtain at the end of the solution of the minimization problem for different values of the number of moment constraints that we use. Okay. So here what you see is that these points tend to locate onto the support of the in the vicinity of the support of the exact solution of the exact optimal transport problem. So that's a nice thing, even though we cannot prove it. Okay. And we've done tests with several electronic densities, so still in 1D, to get this reference, and we observe the same kind of trend. Okay. And what we've done, so here we have no ideas of the quality of the approximations that we obtain. But what is nice is that at least we could run the stochastic algorithm I've told you about in a case where we've got a large number of electrons, 100. So here we've used the 52 polynomial test functions as the moment functions, okay? And the electronic density rho was the sum of 6 quotient functions in R3. And here, so what we are plotting are various 2-dimensional marginals of the approximate measures that you obtain. So typically in the regions where you see a dark blue color are regions where the points tend to concentrate. Okay. So we are not sure. We don't know whether these quantities are approximation of the exact of the solution of the exact problems. What we can say is that we tried several runs of the algorithm with different initial guesses. And if you compare the different solutions that we obtain from each of these runs, in the Wasserstein distance are quite close to one another. So this is reassuring, even though we cannot guarantee it from a theoretical point of view. So there is still work to do in order to let's say to certify this kind of methods. But at least this sparsity structure, it's amenable to some numerical methods that can be carried out in high-dimensional contexts. So that's our motivation for pursuing our research efforts in this direction. And so, sorry, I just wanted to point out, this was in the case of the classical optimal transport problem. And the same sparsity structure in the case of the quantum optimal transport problem, we would like to try also to exploit it from a numerical point of view, but this is still work to do, work in progress. And so just some conclusion. So here we've used some constrained stochastic gradient schemes in order to solve these optimization problems that we obtain with these sparse structures, with no theoretical guarantee on its convergence. So that's where we would really like to interact with people that are experts in this kind of algorithms and techniques to help us devise some more evolved methods than the ones that we use, and things that would be hopefully that could have better warranties, okay, at least on the theoretical side. And there are also lots of open questions related to it. We've got some partial answers into some particular test case. In particular, how should we choose the moment functions, and what is the error that we do when we use the approximate moment constrained approximation with respect to the exact problems? So we've got some partial answers in the case of 2 electrons, but nothing very general at the point. And just wanted to mention that there are some PhD and postdoc positions available at CERNIX related to this kind of problem. So I'm doing some ads. So if people are interested, don't hesitate to come and see. And thank you for your attention.